So, which isotope corresponds to an element with 24 protons and 28 neutrons? Well, 24 protons, atomic numbers in the lower left. B is the only one that has 24 protons. A shows 52 protons. C shows 28 protons. D and E show 52 protons. The atomic number is lower left. The mass number is the upper left. They didn't give you the mass number here, but to find the mass number, we take protons plus neutrons. So what's 24 plus 28? That is 52. So we'd expect 52 in the upper left for the mass number, because that's protons plus neutrons. Because the mass of a single atom is so small, it is inconvenient to use this as a mass unit. Therefore, atomic mass units were invented, and we use carbon-12 as a standard. One atomic mass unit is 1/12 the mass of one atom of carbon-12. So one atom of carbon-12 is 12 atomic mass units. And that converts to grams. One atomic mass unit is 1.6606 times 10 to the minus 24 grams. And again, all periodic tables use atomic masses based on the carbon-12 isotope. Since most elements are a mixture of isotopes, and if you have a chemical sample big enough to see, you have trillions upon trillions upon trillions of atoms, the atomic mass is typically a weighted average of all the naturally occurring isotopes of an element. For example, copper. If you look on your trusty periodic table, you'll see the atomic weight is 63.546. And the masses listed on the periodic table are called atomic weights because they're weighted averages. Because there is no such thing as an atom of copper which weighs 63.546. Copper comes in two major isotopes, 63 and 65. To find the weighted average, we take the mass of the first isotope times its percent abundance in decimal form. Remember, when you convert a percent to a fraction, you divide by 100. Because think about apple pies. If you eat 50% of an apple pie, you ate 1/2 an apple pie. So 50% is the same thing as 1/2. You divide 50 divided by 100 to get 0.5, 1/2. Likewise, 69.09% divide by 100, 0.6909. 30.91% divide by 100, 0.3091. When you convert percentages to decimals, you divide by 100 because 50% of an apple pie is 1/2 of an apple pie, which is 0.5 of an apple pie. And basically, for all the isotopes, you just take the atomic mass of that isotope times its percent abundance, plus the mass of the next isotope times its percent abundance, and do that for all the isotopes, and you get the weighted average for that element. So if we run it through a mass spec, you'll see the actual individual atoms of copper either weigh about 63, just a little bit less than 63, and just a little bit less than 65. But none of them show up at 63.55, because again, that's just a weighted average. But that works well in chemistry because chemical samples have so many trillions of atoms, it all averages out, because you get so many of each type. So silver exists as two major isotopes with atomic masses of 106.9041 and 108.9047. So determine the average atomic mass for silver if the percent abundance for each isotope is 51.82% and 48.18%. And again, we take the mass of isotope 1 times its percent abundance, divide by 100 to convert to a decimal. Pull off the mass of isotope 2 times the percent abundance, and again, you take the percentage divided by 100 to make it a decimal, and we get 107.8680, and that's actually what's listed on the periodic table. Even though no single atom of silver weighs that, it's the weighted average. And because chemical samples have so many trillions upon billions of atoms, weighted averages work really well in chemistry because it all averages out. Here, chlorine exists as two isotopes, chlorine 37 and chlorine 35. And they give you the percent abundance of each. And they actually give you the weighted average. So what they want you to do is find the mass of chlorine-35. So now this takes a little bit of algebra, because we know the mass of the isotope 37 times its percent abundance, because they gave that to you. 24.47 divided by 100 gives you 2.2447 times the mass of isotope A times its percent abundance equals the weighted average. From here, we just isolate the variable and solve. You get 34.97 atomic mass units. And that is the end of that chapter. A good tip here is isotopes always weigh a little bit less than what you'd expect. So chlorine-37 is 36.96, just shy of 37. Chlorine-35 is 34.96, just shy of 35. Let's go back. Silver-107 weighs 106.9. Silver-109 weighs 108.9. Copper-63 weighs 62.92. Copper-65 weighs 64.92. The mass is always a little bit less than what you'd expect, because when you form a nucleus, a little bit of mass is actually converted into nuclear energy. So if you separated the 65 protons and neutrons, it would weigh 65 atomic mass units. But when you put them all together and they form a nucleus, a little bit of that mass is converted into nuclear energy, and so you lose that mass and it's locked into the energy. And so you're actually seeing smaller than expected masses because a little bit of that mass is converted into the nuclear strong force, which holds the nucleus together. And that's the end of chapter 5.